Okay, so let's start our class. Good morning. So we continue talking about so last Wednesday. Apologies again, I forgot to send the notes. So I've sent the slides for the previous one. I'm going to send this one today. I want to go through the class first. Okay, so we started talking about spontaneous process. That's a process that occurs without the need, any external need. It just goes on its own. In a bid to understand what spontaneous processes are in the experiment, these are examples of all spontaneous processes. If you put a ball, it will roll down a hill, but it will never roll back up. If you put an iron, it will rust, forming iron oxide, but iron oxide will never go back to form iron and oxygen. If you put two objects close together, one hot and one cold, the heat will flow from the hotter one to the colder one. It does not flow in that direction, regardless whether you are putting a hot spoon inside cold water or you are pouring the cold water on the hot spoon. The heat flow will always be in that direction. So what's noted is that in the case of the ball, the energy is flowing to a lower potential, higher to a lower potential. This is so this has this flow of energy. In the case of the ion, this is a reaction going on. You're giving it to the surrounding, so we have a flow of energy as well. We recall that in thermodynamics, we partition the universe into system and everything around it called surroundings. They all make up the universe. And whatever happens in the system affects the surroundings one way or another, except you are dealing with an isolated system that's not interacting with the environment. When you put a gas inside a container, the gas molecules move randomly and so they form a uniform distribution. This uniform distribution corresponds to randomness. So you are flowing, the flow of energy is in the direction of randomness in this case. Same thing, the heat flow is also flowing towards a random state. It's not it's not ordered. It's not, when you're looking at something ordered, it's about putting other external forces in play to keep the place ordered. So in general, exothermic reaction releases energy. In releasing energy, you are introducing more disorderliness. However, that a reaction is exothermic does not necessarily mean it is spontaneous. For example, if you lower the temperature below 0 degrees, you move towards formation of ice. And if we look at it, ice looks more ordered than water. However, it is still a flow towards, it's still a random flow in the sense that at that temperature, as you are forming ice, you are releasing heat to the surroundings. No, that doesn't make sense. So let's see, freezing releases heat and increases total disorderliness. That is below 0 degrees Celsius. So with that, we conclude that being exothermic does not necessarily mean being spontaneous. So what do we do with spontaneity? Something that is spontaneous. A new the common theme here is you're moving towards randomness or disorderliness. So, okay, now this slide was supposed to come before that one. A reversible process that can be reversed and irreversible. One thing that we note in all those processes that we looked in the previous slide, they are irreversible, meaning that they don't just go back in the direction in which they come from without an external input. And in some other case, they might be impossible. So this is the slide that I was expecting. The flow of randomness, the flow towards randomness was now described by another entity called entropy. It is related to heat flow, it's related to temperature, but it is not enthalpy. Enthalpy has been described as the total heat content of a system. And when you change the system, the heat content either flows out or it comes in. So, but for a reaction, we're now looking at, so that's just the definition. It's not been, for enthalpy now, it's not been defined for a spontaneous process. So entropy is now defined to account for the measure of amount of disorderliness or randomness that a system likes to undertake. It is related to a flow in randomness. So we define entropy, given the symbol S, as a measure of the amount of disorderliness or randomness in a system. It was coined by this guy in the 19th century when he believed that there's a ratio, there's a relationship between heat and temperature. The several motions in the molecule contribute to entropy, much like they contribute to the internal energy. Aroyeun and Tolulope Oluduro, please mute the mic. So it is related to the entropy is related to the several modes of motions in the molecule. We recall the modes that we looked at were translational, that we mentioned. Translational, that's motion on a straight line. Translational. Rotational, that's a rotational about a point. Vibrational, all this happens in the molecule, and this contribute to energy, and they are also related to the enthalpy. Shalom, Aroyeun, Adeola, Adeola, whichever one it is. And Esther, mute yourselves. It is a state function in the sense that it only depends on the state. It does not depend on how the state was achieved. So that's the way. So then, because of this conviction for Clausius, so for an isothermal processes that you're looking at when the temperature is kept constant, the change in entropy from an initial state is related to the heat for a reversible process divided by T. Reversible, in other words, a slow process that can be easily brought back. So is a small change or small change that you can easily revert. For example, an example of a reversible process is when you're changing phase. So phase is from either solid to liquid or solid to gas or back forth. So when you're changing this phase, when you're changing the phase, the temperature is usually constant. And there's an heat flow, but there's a constant heat flow, whether in the positive direction or in the negative direction. So the measure of the change in entropy for that process is given by Q of air. So why do we say it's a reversible process? Because solid does not change to liquid all at once. I'm sure you have seen that if you put ice outside, it does not turn to water all at once. It gradually changes to water. So that process, more often than not, is a constant energy process. If you keep it in a closed system, it is a constant temperature system. Sorry, not constant energy system. To further understand the idea of entropy, we look at how you can arrange a system. So in a system of four particles that are placed, so the particles can move on their own. So let's call them like gas particles. Gas particles have enough energy to move randomly about. So in a system of four particles that are put in two valves connected by a line or a tap, if you open the tap, the possible arrangement that you can have as for just two, so we're looking at, so the possible is that you have all four here or all four there. That's one possibility. Another possibility is that they are split into 3 and 1. So you have the 3 and 1 here and 3 and 1 here. So 3 in this box and 1 in the other box. Now, the possible arrangement of this one is the particles moving. There are 4 ways in which this can be arranged. So the particles have been labeled A, B, C, D. So A stays in, let's label valve 1. So this is valve 1 and this is valve 2. 1, 2. So you can have all particles A, B, C, and D in valve 1 or all particles A, B, C, and D in valve 2. Then you can have 3 particles in valve 1 and 1 in valve 2. They are not, they are indistinguishable, they are identical, but we can try to label them like we do in some experiments when trying to understand the nitty-gritty of things. So when you label them, you note that even though you are seeing 3 in valve 1 and 1 in valve 2, from time to time, the identity of those particles change. So that gives us a possible number. The number of ways that we can have this is 4. Then you can also have 2, 2 in each case. And then we see that the possible number of ways that you can arrange this is there. So the possible number of ways that you can arrange something is called microstates. A microstate refers to a specific arrangement of configuration. So this is a microstate, 3 microstates. This is 1 microstate. All these arrangements, these ones are the microstates, and these are the several arrangements. If you look at arrangement 1, the number of possible microstates that you can have is 1. When for arrangement 2, where 3 of them are in valve 1 or vessel 1, and 1 is in vessel 2, there's only 4 possible ways in which you can arrange it. If I were to ask you now that given for these particles moving freely, which one will most likely occur at a certain point in time? That will be the arrangement 3. That's the uniform distribution due to the random motion of the particles. So entropy, what we have described here is related to entropy. Entropy is related to the number of microstates, possible microstates that you can have. The higher the possible arrangements that you can have for certain microstates, the higher the entropy for that arrangement. So we relate entropy to microstates. Microstate is given this symbol omega. Depending on the book that you get, some use the symbol W. And Kb is called Boltzmann constant, Kb or K. The more the microstates that you have, the more disordered the system is. Because see, you can have A, B here, and before you know it, B goes there, C comes there. There's freedom of movement. So there's a lot more disorderliness, or what we can call randomness. So the more microstates that you have, the higher its entropy. So you have a higher entropy here. Now, the arrangement that we have shown here is not exhaustive. You can add several another type of arrangement. So what are we trying to what are we trying to get to with this? Is that entropy increases with microstates, possibility of randomness. So microstates, an arrangement, and you can have several microstates. The more microstates that you have, the more entropy you get. For the microstates that we described the other time, each thermodynamic state has a specific number of microstates, and the entropy of that system is given by this equation, S equals K ln K. If there's a process change, that will be the final microstates minus initial microstates from loss of indices. This is given by that. If you look at this equation carefully, you would notice that as the number of possible microstates increases, so going from initial to final, if you're going from a lower number to a higher number, delta S will increase. So as the number increases, as the number of microstates increases, the change in S becomes more positive. And you can see this when mixing two substances to get together. What you notice, there's an increase in randomness of the system, unless all conditions equal. So formation of solution is favored by mixing, increase in entropy associated with mixing, which is what we observe anytime we do reactions. From another point of view, so this is the last one, we're relating entropy to microstate, number of possible states. So we said entropy is affected by motion. So translational motion, vibrational, and rotation. Temperature increases this motion. So if you increase temperature, you increase this internal motions of the molecule. So what are we trying to say? In a gas molecule, your motions are freer, more than in liquid, more than in crystalline solid. As a result, you have the entropy of a gaseous state greater than entropy of a liquid state and greater than entropy of solid states. And we know that this is increasing temperature. So as temperature increases, there is a tendency that your entropy increases. So because of that, the entropy of a system increases when gas is formed from either solid or liquid. When it's formed from solid, we call it sublimation. And when it's formed from liquids, evaporation. Oh wow, it's almost 9:30. And we still have a lot to look at. So also, entropy increases when liquids are formed from solid. In the reverse direction, entropy will reduce, like it's indicated here. So long and short of what we have looked at now is that entropy increases with increased microstates. And if you increase the temperature, entropy also increases. If you increase the volume of the system, you give the particles more room to move. It increases randomness, so entropy increases. And if you increase the number of particles that are moving, entropy also increases. The other way, it will decrease with all these conditions as well. So that's a summary of a quick summary of the characteristics of the new states function entropy. According to the second law of thermodynamics, so second law of thermodynamics is trying to bring us closer to understanding entropy and spontaneity. It states that the entropy of the universe increases for spontaneous processes, because spontaneous processes, they are moving towards uniformity or randomness. And the entropy of the universe does not change for a reversible process. Reversible process, a slow process that you can easily you can easily restore the process. In the field of chemical equilibrium, I just want to make a quick distinction. In the field of chemical equilibrium, when you're talking about a reversible reaction, you're talking about the fact that the rate of the forward reaction is equal to the rate of the reverse reaction. Now, this is different in this case when we're talking about a reversible process in thermodynamics. A reversible process is a process that changes very, very minimally, such that you can easily revert to your original condition. I gave an example in the last class that if you have a class where you have 1,000 people, a reversible process will be one in which one person leaves at a time. If one person leaves at a time, you can easily bring back the person. Unlike an irreversible process, when you say class is finished and everybody just goes towards randomness. So that's why we say spontaneous reaction is an irreversible process. People just, there's nothing holding, you just go. So the concept of reversible reactions, please, is not what we are looking at in this case. Okay, so what did we say? For a reversible process, the entropy of the universe is equal to 0. For an irreversible process, entropy of the universe is greater than 0. Because entropy is a state function, and we know that the universe is made up of system and surroundings, the entropy of the universe is always equal to the sum of the change in entropy of the system plus the change in entropy of the surrounding. So if one of them is positive, the other one will be negative. Long and short is natural process tends to move states with higher entropy or greater disorder. Recall from our first law, energy is constant, of the universe is constant and is conserved. Here, entropy is increased for the universe. Anytime we are looking at excuse me. So this is what I just said now. So when the entropy of the universe is positive, entropy increases and the process is spontaneous in the direction written. When universe is negative, the process is spontaneous in the opposite direction. So this is a process A going to B. So if it's positive in this direction, if delta S is positive, that means it's spontaneous in this direction. If it is negative, positive. If it's negative, delta S is a process is spontaneous in the other direction. If everything is 0, so you're saying the system is in equilibrium. So when you want to describe a system in equilibrium with respect to entropy, an equilibrium is a state where the change in entropy is equal to 0. So that's one definition for a system in equilibrium. So let's look at entropy changes for the surroundings. Entropy change for the surrounding will be negative of entropy change for the system. we so when it flows out of when it flows through the boundary during a process, the delta S of the surrounding is determined by the flow of it, the direction of the flow of it. We know that for an isothermal process, the one that we mentioned the other time, so where we said that delta S equals Q reversible over T. So that's for the system. Delta S of system is equal to minus delta S of so sorry, don't let me put it that way. If it flows out of the system, the negative if it is absorbed by the system, if it of the system is positive, then you have an equal minus Q for the surrounding. So if Q is for the system, Q reversible is for the system, then we know that that of the surrounding is minus Q of the system divided by T. At constant pressure, we already said that the heat content is the same thing as delta H. So the delta H for the surrounding can be defined as minus delta H of the system divided by temperature, isothermal process. So the sign of the surrounding will depend on the direction of the flow of heat. If it's an exothermic process, delta S will be positive for the surrounding. An endothermic process, so at constant temperature, delta S surrounding, delta S will be positive. Recall, delta H is negative for an exothermic process for the system. So that's why for the surroundings, it is positive. And for the endothermic process, delta S surrounding is negative. So the magnitude of delta S will depend on the magnitude of Q. So we can't easily mention that. Okay, so we want to define another concept, free energy, that also helps with to determine the spontaneity of a reaction. So we already said that delta H of the system of a universe, delta S, the entropy change of a universe is equal to the entropy change of the system plus the entropy change encountered in the surrounding. In the last slide, we defined the entropy change of the surroundings as minus delta H of the system divided by T. For a spontaneous process, delta S universe increases, like we already said. If you multiply by T, and minus 1, T comes here, minus T delta S minus T delta system plus delta H of the system. So we have a relationship that relates delta H of the system and the entropy change of the system together. Arrange it simply as delta H of the system minus delta T of the system. Now this quantity is referred to the change in free energy of the universe. That's because the free energy is defined, as H plus T, H minus Ts, not H plus Ts, not H plus T delta S. Let's look at it in a better way. Delta S of the universe is defined as the change in Gibbs free energy and Gibbs free energy is given the delta G. When delta S of the universe is positive, which we say that's the one for spontaneous process, then delta G is negative. Therefore, our delta G for a spontaneous process is negative. What is the free energy? So the free energy is a fundamental concept used to predict the spontaneity of a process. That was where the concept came from. And why did we try to relate everything? We realized that the flow of it helps to determine free energy, or not only the randomness, because we realized that the flow of it in one direction can be spontaneous. The flow of it in the other direction can also be spontaneous, depending on the nature of the temperature. So free energy so the energies is a system's same thing, energy to perform work or transfer it. Energy is a capacity to do work or transfer it. The free energy on its own is defined as a energy available to perform work at constant pressure and temperature. And again, it is useful to determine the spontaneity of a process. Okay. So we've been able to, sorry, if delta G is negative, the forward reaction. Somebody has their mic on. So if delta G is negative, so you're looking at a process A going to B, and if delta G is negative, that means this reaction is spontaneous. If it is positive, is the reverse reaction that will be spontaneous. What about if it is zero? The system is at equilibrium. So system at equilibrium, delta S is zero, delta G is also zero. It does not mean that delta H is zero. What equation is this? Ma, what is the equation again? Please, Ma. I don't know the equation she's referring to. Tijani Akintunde,
Ma,
I do need to understand your question.
I said the previous slide, ma, where you were defining free energy. I'm trying to note that down.
Oh, okay. So that means I've answered your question.
No, help me to return it. It's not this one, ma.
This one?
Yeah, thank you, ma. Yes, ma. Yes, ma.
Okay. Okay, so let's move on. So that brings us to the third law of thermodynamics. The entropy of a pure substance, crystalline substance, at absolute zero is zero. Okay, so I'm supposed to use omega here. So if that is zero, so think about it. An absolute substance at temperature of zero, absolute zero is a 0 Kelvin. What is 0 Kelvin in Celsius? That's about -273.
-273.
Exactly. So at that
17.
temperature, nothing is moving. Absolute zero. If you want to read about absolute zero, you can read about it. Entropy at that state is zero. Nothing is moving. There's only one way in which you can arrange the system if you consider it from the point of view of microstates, and if you consider it from the point of view of molecular motions, nothing is moving. So entropy is zero at that point in place. So a little bit more about entropies and free energy. Just like delta H of formation, several standard entropies have been calculated for several substances, and then you just need to check the reference and know the answer. How is the standard entropy defined? So standard entropy or molar entropy, that's the entropy at 298 Kelvin. So you can look at it as the entropy change from 0 Kelvin to 298 Kelvin. That is the amount of disorderliness that occurs for the substance. That's what is being reported for standard entropy. Looking at it, let's see, it tends to increase with molar mass, which is expected. Not an absolute statement, but usually it tends to increase with molar mass. From reference for entropy is zero, just like we said for the third law of thermodynamics. So the reference values for elements are not zero. Reference values for delta H for elements are usually zero. For the reference delta H for elements are usually zero. I just want to write what I just said now. Reference entropy is zero. For entropy is zero. That's at 0 Kelvin. So since we are looking at the reference entropy at 298, it is not zero for elements. So that we do not confuse those two things together. You can calculate change in enthalpy for processes, because enthalpy is a state function just by final minus initial. So we can also use this table of values to calculate change in entropies or expected change in entropies that we are anticipating. Large molecules also tend to have greater entropies. This is for propane and this is for methane. So larger molecules also tend to have higher entropies than smaller molecules. As long as it is a tendency towards disorderliness. So I like including both, or randomness. You can actually liken it to the way we do things. The lesser the number of laws available, the more people will behave randomly. If you are driving and there's no street lights, no anything, what happens? Chaos. So entropy measures the tendency towards disorderliness, randomness, and or chaos, because it leads to chaos when you don't have laws. So you can also calculate the change in enthalpy, just like I said because it's a state function. Change in enthalpies of a process, of a reaction, can be calculated by the enthalpy, sum of enthalpy changes of the product standard minus sum of enthalpy change of the reactants. We should have some worked examples somewhere around here. Yes. For example, calculate the change in entropy associated with the ABA process. The ABA process is the process for the production of ammonia from nitrogen and hydrogen. It's a process that's been studied for many years so that we know that it's economically viable. So given that the standard entropy for ammonia is 192, for hydrogen is 130, and for nitrogen is 191. So from the equation, delta S is sum of delta S of products minus sum of delta S of reactants multiplied by whatever the stoichiometric ratio of the product of the species are. So for example, delta S will be 2 times S of ammonia because you have 2 moles of ammonia minus sum of that of N2 and H2 times 3. If you plug in your equation, you have minus. So we see that this is not a spontaneous process. If you want to look at economics of things and your process is not spontaneous, there are other conditions that you consider. We can also talk about the standard free energy of formation or standard free energy change of formation. So that's the Gibbs free energy change when 1 mole of a compound is synthesized from its constituent elements in their most stable forms. So by now, you know that when you're talking about standard in the field of thermodynamics, the standard change in enthalpy, that's enthalpy change when you form this, standard entropy too, enthalpy change from 0 to 298 and all that. So all from their constituent elements. So delta G of formation of an element in its standard state is 0, analogous to the delta H of formation of elements. Different from delta S of elements. Delta S of elements is not 0. But delta G of formation of an element and delta H of formation of an element is 0 in their standard state. And for a reaction, you have it as that of the sum of the products minus sum of the reactants. Okay. Free energy changes at other temperatures. Free energy changes at other temperatures can be calculated using this expression. So let me go back to the other slide. If you are given a reaction, your delta H of formation is given as that. If you need to consider it for other reactions, for other temperatures, you have the delta G of formation at this temperature. What happens at another temperature? This is the expression, and we have the same expression right here. So how does delta G change with temperature? Delta G changes with temperature by its temperature dependence term, T delta S. So let's look at this critically. We have talked about spontaneous conditions, and we have realized that the spontaneous condition depends on temperature. It depends on experimental conditions and all that. So if you're looking at usually at a constant temperature process, more often than not, you measure all this at a certain temperature. Once the temperature changes, the value changes. Okay, so you can have an exothermic reaction with positive delta S. That's a spontaneous exothermic reaction. So you see, it is spontaneous at all temperatures. It doesn't matter. If we look at an exothermic reaction that is not spontaneous, there's a possibility that delta G will be positive or negative. Such processes, they are spontaneous at low temperature but not spontaneous at high temperature. For example, if you're converting water to ice, water to ice is an exothermic process. What am I saying? Sorry. If liquid goes to solid, what happens? Yes, it's an exothermic process. Depending on the temperature, it can be spontaneous or not spontaneous. So that's what happens when you have a conflicting sign for delta S and K. Now, if your system is endothermic, if your process is endothermic and delta S is negative, delta S negative means that you are moving towards disorderliness. That process is not spontaneous at all, regardless of the temperature. But for an endothermic process that is moving towards randomness, temperature might affect it. Temperature will also affect that. So whether your whole process will be spontaneous or not spontaneous will depend on delta H, delta S, and temperature. All these are present in the Gibbs free energy change. But more often than not, a negative delta G is used to determine a spontaneous reaction. Yes, so if you look at it, when it is negative, it is spontaneous. That would be at high temperatures. When it's negative, it's also spontaneous at low temperature and at high temperature. So delta G, since reactions are spontaneous, so the sign of entropy and the magnitude will determine the spontaneity of the reaction. But delta G is spontaneous. The reaction is spontaneous if your delta G is 0. That depends on the relative magnitude and sign of delta H, delta S, and temperature. Okay, I think I just have a few more examples to work out. Use the information below to determine if NH4NO3 will dissolve in water at room temperature. Okay, so if you look at NH4 solid will dissolve in water, that means you're saying that, so that's the reaction. If you put this in water to get this plus that. We're not given delta G, so we cannot say whether, we can't say it off of our head. Delta G is not given, but we are given delta S of formation and delta H of formation. So we can calculate delta G from the given value. So how do we go about it? Let's calculate delta H first. I should have brought so please, I can't quickly do that, but I'm going to use the values given here and this equation to calculate our reaction, given that for a state function X, for a reaction, that will be delta X of products minus delta X of reactants, or X of formation, sum of delta X of formation minus of products minus sum of delta X of formation of reactants. So put that at the back of your mind while we solve that. So delta H of formation of products minus reactants, NH3, the product is a NH4 plus and NO3 minus NaNO3. Okay. So this is our reactant and this is our product, 1 mole NH4 plus. So this should be NH4 plus, not NH3. So we calculate our delta H to be 28.05. This is an endothermic reaction. We can calculate our delta S too. It is positive, meaning that the forward reaction favors randomness. So using the same formula, so let's calculate our delta G then. Delta G is delta H minus T delta S. So what do we say? I think that the reaction is favorable on the condition that we are given. Will it be fast? That's a totally different ballgame. But calculated delta G is negative, and then it will be favorable. Another example, the formation of water from oxygen is given by this equation from oxygen and hydrogen. Using standard free energies of formation at 298, calculate delta G. Calculate delta G for the reaction. You see, the magnitude is high, so it means that the process is spontaneous under standard conditions. Okay, so what's the time? Yeah. Let me quickly round this up because another teacher is coming on Monday. At constant temperature and pressure, under standard conditions, we can also calculate our delta G, free energy. So this is our standard free energy. So you're looking at considering it at another point in time, plus RT ln Q. And I actually have another class now. What is the okay, so let me just quickly round up. So when you're relating to equilibrium, you know, equilibrium is have you done equilibrium, please? Chemical equilibrium.
No, ma.
Okay,
No,
so
ma.
this
No, ma.
No.
I
No, ma.
beg now.
No. No, ma.
No, ma.
Okay. Emma, no, Lord. Once you are done, you let me know.
No, ma.
It's okay, Jaria.
Oh, yeah, me learn.
No, ma.
Rara, ma.
Down again. You
What
don't
team,
do
ma?
it. It's that one.
We can relate free energy to equilibrium. In the field of equilibrium, equilibrium talks about how far a reaction has gone. So what does that mean? You start a reaction A going to B, more often than not in a closed system, meaning that mass is not allowed across the boundary.
I'm talking to my
So A goes to B in that closed system. Because it's a closed system, B can go back to A. So once the rate of A to B, which is the forward reaction, is equal to the rate of the reverse reaction B to A, you say an equilibrium is achieved. Q that we have here is a measure of equilibrium.
like joke.
Q is a measure of how far you are from equilibrium. Okay. So at equilibrium, so Q is a measure of equilibrium. Equilibrium constant, I know you have done this in secondary school, is a measure of equilibrium. So its value with respect to, it can be equal to K, it can be less than K, it can be greater than K. So all this will depend whether you have achieved equilibrium or you have surpassed equilibrium. At equilibrium, Q is often equal to K. If that is the K, delta G is 0. Because we already said that at equilibrium, Q equals to K, sorry, not if that is the case, sorry. At equilibrium, our reaction quotient Q, that's what it is called. Is equal to equilibrium constant. So I'm just saying this because you will soon learn, that you have not learned it does not mean you won't learn it again. So you may be able to come back to the video. And one other thing, from time to time, you can send your questions on the YouTube page if you want more clarifications. At equilibrium, our delta G is 0 and Q equals to K. So this energy becomes delta G equals to RT ln K equals 0 plus RT ln K is equals 0. If you rearrange it, our standard free energy becomes minus RT ln K. So this is another way to calculate free energy. And in another way, you can say it is a way to calculate equilibrium constants. So we can relate the extent of a reaction to the free energy of a system. Okay.
Ma,
remaining,
is the how the molar gas constant?
yes, please.
Okay, that's
Depending on the unit you're working
2.3.
on, 8.314 or 0.081, depending on the unit you're working with. So let me
Okay,
write
ma, are we
Sorry.
going to be given the value while solving, ma?
What do you think? It's good now.
Sorry, ma. Please, I have 2 questions.
Number one,
Okay,
I
ma,
have
please,
an
can you please
answer.
repeat? Yes, ma, I'll be fast. Can you please repeat the definition of a reversible process in thermodynamics?
That's not only.
I think there are
Ma,
two
do you hear
teachers
me?
in class. I heard you, but somebody is talking too. So what I said, let me write it here because I'm not going to work this example. It's self-explanatory when you get it. So we say a reversible process. It is a process that occurs slowly. And there's this big word that we often use. The changes are, the big word is infinitesimal, meaning small or negligible. That is a reversible process. And the example that I used before, I'm going to use it again. If you have a number of people in a place and one person leaves, you can easily bring back that person. That is a reversible process. Yes,
Okay, ma.
ice to water is reversible in the sense that it changes slowly. Here you
Oh,
get.
yes, ma.
So ice to water is, she said if it is positively, it will be moving in the same direction. I don't understand that one.
No, ma, like,
Ma, please,
because
will you drop the
Gibbs free energy,
slide?
because Gibbs free energy is in thermodynamics. But when you say is positive, when Gibbs free energy is positive, it is spontaneous in the reverse direction, right? So that
Yes.
reverse direction, we're not talking about reversible process, right?
No. So
Okay.
that's
Ma, please,
so
after
we're
the
going,
class, will you drop the slide?
yes, please. So this is a forward reaction. This is a reverse reaction.
Okay. Yes, ma'am. Thank you, ma'am.
Okay. Okay. Let me quickly go through this. I have another class waiting for me. Calm down. Can you please repeat the definition of reversible process for Gibbs free when we talk about data GP? Okay, that's the question. I have
No,
a
ma, that's
question.
me.
Can you please repeat? What is wrong with you?
No, ma, that was me. No, ma, that was me.
No, you said you repeated that question 20 times.
Sorry, I am.
Okay.
Sorry, ma.
Ma, please, will you drop the slide after the class?
No, I will not drop the slide ever.
Calm down. Let her.
She already answered you now. She said
Apply
yes.
already. Let's see as
Okay. I wish you best of luck in all your endeavor.
Thank you, ma.
I think that's it.
Amen. Thank you.
God bless you, ma.
Thank you.
I love you, ma. I love you so
Thank you,
much.
ma.
Oh.
Thank you.